This is section 3.3 on the unit circle and circular functions. We've learned so far how to find trig functions of angles, and the angles could be either in degrees or in radians. Now we're going to take trig functions of real numbers. Now if you look at the circle here, the unit circle is x squared plus y squared is equal to 1. And the reason why it's called a unit circle is because the radius is 1. Because remember, x squared plus y squared equals r squared is the equation of a circle, and r squared is 1, so that means r is 1. So it's 1 unit for the radius. Now, do you remember the formula from the last section, s is equal to r theta? Well, if r is equal to 1, then we have s is equal to 1 times theta, or s is just equal to theta. So s and theta are the same number as long as r is equal to 1. So if you look at the circular functions in the box, you can see another definition of trig functions. This is our third set of definitions. And in this case, instead of using theta for an angle, we're thinking of the letter s for any real number. And when you're taking calculus, this is the type of function that you're going to be working with, where the input is a real number instead of the input being an angle. Now you'll see that all that you've learned so far, you're just going to use the same thing, and it's just looking at it in a little bit different way. So if we look here, do you see how sine of s is equal to y? If you compare that with the definition in chapter 1, it was y over r, but in this case r is 1, so that's why it's just y over 1. Cosecant is the reciprocal of sine. Cosine, before we had cosine theta is equal to x over r, again r is 1, so now cosine of s is x over 1, which is x, and secant is the reciprocal. And then tangent of s is y over x. You see that that's the same as what we had in chapter 1 because there's no r involved, and cotangent is the reciprocal of that. So for the unit circle, you've already memorized something that looks like this that just had the angle measures. Now if we restrict the circle to be a unit circle, that means that r is equal to 1. And so do you see how we have ordered pairs here? And on the quadrantal angles, you can see we have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. We also have the special angles here. So you remember that the special angles are either multiples of 30 or multiples of 45, except for the quadrantal angles. So those are the special angles that you've seen so far. If you have other angles, up to this point, you would just use a calculator to find the trig function values. But for the special angles, we have nice numbers for our trig values. And let's take the 30-degree angle. Suppose that we draw a triangle straight down. Remember, we always draw it to the x-axis, never to the y-axis. So a right triangle straight down. Let's compare that with what we've learned so far. So remember, if we have a 30, 60, 90 triangle, remember how the 30 degrees is opposite of the side 1, and 60 degrees is opposite of root 3, and then 2 is the hypotenuse. Well, if we compare what we have here with this point, do you see how this point is root 3 over 2, 1/2? And then for the triangle that I drew inside the circle, the radius is always 1 because it's a unit circle. Now if we compare the two triangles, do you see how they are similar to each other? We're just taking this triangle that we already learned, and then we're dividing each of these by 2 because it's just half of the size for the circle that's inside of the circle. So then we have root 3 over 2, and you can see that's what x is, and then we have 1/2, and that's what y is, and then the radius is equal to 1, because 2 over 2 is 1. So these points here, that's where they come from. They're similar triangles to the triangles that you've already learned. It's the same idea with the 45, 45, 90. So I'll draw a triangle here for that one. So again, the radius is 1, And if we draw the triangle here, It's the isosceles triangle. It's a right triangle. So this is 45 degrees for both of those angles. And then we have 1, 1, root 2. So for this one, again, we can compare this with what we have here. Do you see how the radius is 1 on the unit circle? So to make this 1, I'm going to divide each of these by root 2. Now if we compare this, you see that the hypotenuse is 1. And if we rationalize the denominators for each of these, then we get this ordered pair here for x and y. So I can multiply this by root 2 over root 2. And the same thing here. And so we get root 2 over 2 and root 2 over 2 for x and for y. And that's what we've got for this ordered pair. So that's the unit circle. Now, hopefully you see some symmetry in the unit circle. So do you see how here we have 1, 0. If you go straight across the y-axis, we have negative 1, 0. And that goes with all of these points here. What that means is the unit circle is symmetric with respect to the y-axis. So if you fold it over the y-axis, you see you have the same thing on both sides. Do you see also that it's symmetric with respect to the x-axis? If you compare this root 3 over 2, 1/2 with the root 3 over 2, negative 1/2, do you see how, and the same thing with all of these other ones, if you fold the paper across the x-axis, then you can see that you have the same thing on both sides. So it's symmetric with respect to the x-axis, and it's also symmetric with respect to the origin. If you compare something like root 2 over 2, root 2 over 2, with negative root 2 over 2 and negative root 2 over 2, and then the same thing with all the other points, you can see that across the origin, there is symmetry. So let's go ahead and write that in the next page here. So the unit circle is symmetric with respect to the x-axis, the y-axis, and the origin. If a point AB lies on the unit circle, then so do A, negative B, and that's because of symmetry across the x-axis, negative A, B, that means there's symmetry across the y-axis, and negative A, negative B, because it's symmetric with respect to the origin. Furthermore, each of these points has a reference arc. Of equal magnitude. So let's look at an example of the reference arc. We're going to take a reference arc of pi over 3. So with a reference arc of pi over 3, you see here s is equal to pi over 3. If we look on the unit circle for pi over 3, we see that's right here. That is in the first quadrant. The symmetry type and the corresponding point. Okay, well, what is the corresponding point? That is 1/2 root 3 over 2. And then cosine of s is defined to be x. So looking back at this definition, cosine of x is x. So the x value is 1/2. And then sine of s is y. You can see that by the definition. So sine of s is root 3 over 2. Now you could have found this using methods that we learned in previous chapters, but now I want to practice using these definitions. Another angle that has a reference arc of pi over 3. Well, if we take pi minus pi over 3, do you see how we're at the unit circle, we're taking pi, which is over here, subtracting pi over 3, and we end up at 2 pi over 3. So that's this angle there. So at 2 pi over 3, the quadrant of s is the second quadrant. The corresponding point is negative 1/2 root 3 over 2. Now if we compare this point that we just found with the original point, Do you see how it's symmetric across the y-axis? So the symmetry type is the y-axis. The cosine of s is the x value, so that's -1/2. And sine of s is the y value, that's √3/2. We go to pi plus pi/3. So we start off at pi on the unit circle, we're adding another pi/3, we end up at 4 pi/3. This is in the third quadrant. The corresponding point is -1/2, -√3/2. And then the symmetry type, well, comparing that with the original point, do you see how it's symmetric across the origin? So that's the symmetry. Cosine of s is defined to be the x value, so that's -1/2. Sine of s is the y, so that's -√3/2. And then for the last one, we have 2 pi, so that's over here. If we take away pi/3, we're down at 5 pi/3. This is in the fourth quadrant. The corresponding point is 1/2, -√3/2. Comparing that with the original point, we have symmetry across the x-axis. Cosine of s is the x value, so that's 1/2, and then sine of s is the y value. So I've made this very small so we can see both of these pages. If we look at the next part, because cosine of s is x, sine of s is y, then if we take the equation of a unit circle, which is x squared plus y squared equals 1, then we can replace the x with cosine and the y with sine. So we have cosine squared plus sine squared is equal to 1. And that should look familiar to you because it's a Pythagorean identity. In the next box, it's talking about the domains of the circular functions. So the domains are the values that s can be. So for the sine and cosine functions, s can be any value, but not so for the rest of them. And the reason why is because of the restrictions. So if we go back to the definitions, do you see how for cosecant of s, you cannot have y be 0? And for cotangent, you can't have y be 0. And then for tangent and secant, x cannot be 0. To keep that from happening, let's just look first at tangent and secant. We cannot have x be 0 for tangent and secant. If we look at the ordered pairs that would make the x 0, do you see how we have 0, 1 and 0, -1? And if we think about what 0, 1, where 0, 1 is at, that's at the angle s is equal to pi/2. And at 0, -1, s is equal to pi/2 plus another pi. So that means that x cannot be, I'm going to write this in a little bit easier of a way, at least for me. We can say x cannot be equal to pi/2 plus n pi, where n is any integer. So x cannot be equal to pi/2 or 3 pi/2 or 5 pi/2, 7 pi/2. And that's just for tangent and secant. For cotangent and cosecant, if we look at the definitions, do you see how y cannot be 0 for cotangent and for cosecant? So where is y 0 on the unit circle? Well, you can see y is 0 here at s is equal to 0, and y is equal to 0 at s is equal to pi. So do you see where s is some multiple of pi? Then you're going to be given a y value of 0. That's for this one here, x cannot be equal to n times pi, where n is any integer. So going back to tangent and secant, you can use this, what they have here. This is the same, this 2n plus 1, the quantity times pi/2 is the same thing as pi/2 plus n pi, either one of those. And then cotangent and cosecant, s cannot be some multiple of pi.